Hello everybody, let's take a brief look at mathematical induction. So mathematical induction is a technique used to prove a rule or a formula that relates to sequences and series involving the natural numbers. So the natural numbers are the counting numbers, 1, 2, 3, 4, etc. The numbers that do not include negatives and of course decimals or fractions. So the main goal with mathematical induction is to prove that a particular rule holds for all the natural numbers. The steps in mathematical induction involve first showing that a particular rule or formula is true for the base case. Now the base case could be n is equal to 1 or n is equal to 0. Once you show that it's true for the base case, you then make the induction hypothesis. So this hypothesis is where you assume the rule is true for n is equal to k, and k is any arbitrary natural number. And then what we set out to do is to prove if the rule holds for n is equal to k plus 1. So the natural numbers increase in increments of 1. So if it's true for k and it's true for k plus 1, then it should be true for k plus 1 plus 1, and also k plus 1 plus 1 plus 1, and so on and so on and so on. So that's why once you prove it's true for k plus 1, then you basically prove it's true for all natural numbers. An analogy people often use is that of dominoes. If you have a whole lot of dominoes lined up and you knock one over, the one falls and hits the next one over and hits the next one over, and so on and so on. So I think it's best if we just go straight to an example. So here's the first problem. So use mathematical induction to prove the following. So A is just 2 plus 5 plus 8 plus 11 plus whatever, all the way to plus 3n minus 1 is equal to n times 3n plus 1 over 2. So let's just do that one immediately. Let's do 1a. So let's go for it. Okay, let's begin here with the base case. So the base case, because we're dealing with a series of numbers, there are several terms, and the first term is number 2, is the natural number 2. So the base case in this problem is n is equal to 1. And when n is equal to 1, what's our right hand side? So our right hand side is 3n plus 1 times n over 2. And if we substitute 1 in here, we're going to get 1. 3 times 1 plus 1 all over 2. And if you calculate this, 3 times 1 is 3 plus 1 is 4. Times 1 is 4 over 2, and this is just 2. So it corresponds to the first term in our series. So the base case is true. Now we do the induction hypothesis. The induction hypothesis says assume true for n is equal to k, where k is just some natural number. So this is 2 plus 5 plus 8 plus 11 plus a whole lot of other terms plus 3k minus 1 is equal to k times 3k plus 1 over 2. Now if we notice this series, the terms in the series are increasing by 3. So 2 becomes a 5 when we add 3. 5 becomes an 8 when we add 3. 8 becomes an 11 when we add 3. So we keep on adding 3. So this term here, 3k minus 1, we need to add 3 to get to the next term. So what's 3k minus 1 plus 3? Well, that would be 3k plus 2. So what we can do now is we can say 2 plus 5 plus 8 plus 11 plus a whole lot of other terms plus 3k minus 1 plus 3k plus 2. But what we do on the left hand side of the equal sign, we must do on the right hand side. So on the right hand side, we have k, 3k plus 1 over 2, and now we must add 3k plus 2. Now let's just focus on the right hand side. So the right hand side, let's try and simplify it here. So we have k times 3k plus 1 over 2. Let's put the term 3k plus 2 over 2. So we must multiply the top and bottom by 2. So we end up with 3k plus 2 over 2. Now we got the same denominator, so let's expand these brackets here. So k times 3k is 3k squared plus k, and then 2 times 3k is 6k plus 4, and all of this is over 2. Simplify a bit, we get 3k squared plus 7k plus 4 all over 2. So continuing over here, we have 3k squared plus 7k plus 4 over 2. Now if we factorize this a bit, you'll see we can write this as 3k in brackets and then times k in brackets here. We'll have to just see how to factorize this. So we have a middle term that's 7k, and our coefficient at the end here is a 4. So 4 can either be 2 times 2 or 4 times 1. So to get that middle term of 7, I think we should go with k plus 1 and 3k plus 4. We can just verify that this is correct. Let's just see what we get if we say 3k plus 4 multiplied by k plus 1. Let's see what we get. 3k times k is equal to 3k squared. 3k times 1 is equal to 3k. 4 times k is 4k. And 4 times 1 is 4. And if we simplify further, we have 3k squared plus 7k plus 4. So this factorization was correct. So that's good. So let's further manipulate this. So we'll see we have k plus 1 times 3k plus 4. But 3k plus 4 we can write as 3k plus 3 plus 1. So I'm just writing the 4 as 3 plus 1 all over 2. And if we look more carefully, we have k plus 1 multiplied by, we can factor the 3 out here, and then we have 3 into k plus 1 plus 1 all over 2. So now we have this, we have 2 plus 5 plus 8 plus 11 plus a whole lot of other terms plus 3k minus 1 plus 3k plus 2 is equal to k plus 1 into 3k plus 1 plus 1 all over 2. And we'll see that the right hand side here of this series, where we add an extra term, k plus 1, this right hand side looks very similar to the previous one. So the original series, the right hand side was k into 3k plus 1 over 2. But now with an additional term, so when we added an extra term, k plus 1, notice that the k there becomes k plus 1, and the 3k becomes 3k plus 1, and then everything else is still the same. So we show that the series holds for the next term in the sequence of natural numbers. So if it's true for k plus 1, it will be true for k plus 1 plus 1, which is k plus 2, and then k plus 3 and k plus 4. So it will hold. So therefore 2 plus 5 plus 8 plus 11 plus all the way 3n minus 1 is equal to n times 3n plus 1 over 2 for all n in the natural numbers. Now moving on to question 1b. Here we're going to do, let's look at the base case again. So base case, n is equal to 1. So let's see what we get. We get 1 squared times 1 plus 1 all squared all over 4. So 1 squared is just 1, 1 plus 1 is 2, 2 squared is 4. So this is 4 over 4, which is equal to 1, which is also equal to 1 cubed, because 1 times 1 is 1. So for the base case, for the first term here, 1 cubed, it's true. So now we do the induction hypothesis. So the induction hypothesis is assume true for n is equal to k. Assume true for n equal to k, where k is a natural number. So now what we have is 1 cubed plus 2 cubed plus 3 cubed plus a whole lot of other terms cubed plus k cubed, and this is equal to k squared into k plus 1 all squared over 4. Now we have to show that this is true for k plus 1. So if we look at our series here, we've got 1 cubed, and then we've got 2 cubed, and then we've got 3 cubed. So it's the next number cubed. So if we continue with the sequence or series, we have 1 cubed plus 2 cubed plus 3 cubed plus all the way to k cubed, and then the next number would be k plus 1 cubed. But whatever we do on the left hand side of the equal sign, we must do on the right hand side. So on the right hand side we have k squared plus k plus 1 squared. So k squared times k plus 1 squared over 4. And then we need to add this k plus 1 cubed. So let's just focus on the right hand side here. Don't want to keep rewriting the left hand side. So with the right hand side, let's get the same denominator. So the same denominator will be 4. So the left term stays the same, it's just k squared into k plus 1 all squared. Let me extend this. Plus 4 times k plus 1 cubed all over 4. This 4 appeared here because to put it over the denominator of 4, we have to multiply by 4. So we can expand all this, and but that will be very painful. So what we can rather do is we can factor out k plus 1 squared. So let's see what we get. If we factor out k plus 1 squared, we have k plus 1 squared into, let me make square brackets just to be more explicit. So when we factored out the k plus 1 squared, we're left with k squared plus 4 times k plus 1. Remember the k plus 1 cubed. This was a cubed here. So when we factored out k squared, we're still left with k plus 1. And this is all over 4. So continuing, we have k plus 1 all squared into, and then in the square brackets we had k squared plus 4 into k plus 1. And all of this is over 4. So let's further simplify. So we'll leave the k plus 1 squared as is. And then inside the square bracket here we have k squared plus, so 4 into k plus 1 gives us 4k plus 4. And this is all over 4. So if you look at the square bracket there, that is k plus 2 squared. Let's just verify. So k plus 2 squared is equal to k plus 2 times k plus 2. And if you expand this bracket, k times k is k squared, k times 2 is plus 2k, 2 times k is just plus 2k again, 2 times 2 is 4. So this is very much what's inside that square bracket. So it's k squared plus 4k plus 4. So the top there, we can write it now as k plus 1 squared. I'll go back to round brackets because this is just k plus 2 squared. Now k plus 2 can be written as k plus 1 plus 1. So we can do this, we can say k plus 1 squared multiplied by k plus 1 plus 1 squared. So why am I doing that? We want to write this k plus 1 almost as if it's a separate entity, all over 4. So now if we write out our full sequence here, we have 1 cubed plus 2 cubed, our full series, sorry, plus 3 cubed, all the way to k cubed plus the next term, which is k plus 1 cubed, and this is equal to k plus 1 squared into k plus 1 plus 1 squared over 4. Now if you remember, before we add this extra term of k plus 1, our original series was 1 cubed plus 2 cubed plus 3 cubed plus k cubed equal to, it was k squared into k plus 1 all squared over 4. Now if you compare these two, for example, you go k squared into k plus 1 squared over 4. If you replace it with k plus 1, let's say you transformed it, you would have now, wherever you have a k, replace it with k plus 1. So now you have k plus 1 squared, and then instead of k plus 1 squared, you have k plus 1 squared over 4. So therefore we've proven that 1 cubed plus 2 cubed plus 3 cubed plus all the way to n cubed is equal to n squared into n plus 1 squared over 4, and this is true for all n in the natural number set. Alright, now let's try a different version of the mathematical induction. So let's try to prove that 7 to the power n minus 2 to the power n is divisible by 5 if n is a natural number. So for the base case, let's make n is equal to 1. So this implies that 7 to the power 1 minus 2 to the power 1 is equal to what? Well, 7 to the power 1 is just 7, 2 to the power 1 is just 2, 7 minus 2 is 5, and of course 5 is divisible by 5. So this is divisible by 5. So that was quite trivial. So 5 divides 5. Now we need to do the induction hypothesis. So the induction hypothesis says assume true for n is equal to k, where k is some natural number. So how do we write this? So we're going to say 7 to the power k minus 2 to the power k is equal to 5t, where t is some natural number. So it's important to do this because we can't just say 5, it's 5t, because t could be 1, then we just have 5, t could be 2, then we have 10, 10 is also divisible by 5, 15, 20, 25, so all the multiples of 5. So 5t, where t is a natural number, covers all multiples of 5. And we're going to use this result, so let's name this equation here, equation star. So basically we're saying 7 to the power k minus 2 to the power k is equal to 5t. Let's see what happens when we have 7 to the power k plus 1 minus 2 to the power k plus 1. What is this equal to? So let's write this as 7 to the power k times 7 minus 2 to the power k times 2. This is just the rules of exponents. Now from this equation star, so I can say from star, we can make 7 to the power k the subject of the formula. 7 to the power k is equal to 2 to the power k plus 5t. Just rearranging equation star. We just put that in a little box there just to say we're doing something on the side there. So now here, getting back to our main calculation, 7 to the power k can now be written as 2 to the power k plus 5t, let's put it in brackets, times 7 minus 2 to the power k times 2. And if we go a little bit further, let's multiply the 7 into the bracket. So we have 2 to the power k times 7 plus 5t times 7 is 35t, and then we have minus 2 to the power k times 2. So these terms here are like terms, 2 to the power k times 7 and negative 2 to the power k times 2. Those are like terms. 2 to the power k is the like term there. So we can further simplify. So we have 7 minus 2 is 5, so we have 5 times 2 to the power k plus 35t. Now if I'm not mistaken, 35 is a multiple of 5. So we can further simplify this, throwing the 5 out. And then in brackets we have 2 to the power k plus 7t. So what we've shown here is that 7 to the power k plus 1 minus 2 to the power k plus 1 is equal to 5 times some number. This number is 2 to the power k plus 7t. We don't care what this number is. The fact is 5 is multiplying this number. And any number multiplied by 5 is divisible by 5. So therefore, our induction hypothesis was correct. So therefore, 7 to the power n minus 2 to the power n is divisible by 5. And we are very happy. Okay, let's do the last problem here with mathematical induction, similar to the previous one. So here we're saying prove that 7 to the power 2n plus 1 is divisible by 8 for all n in the natural numbers. So let's look at the base case first. So base case, suppose we could make n 0, but let's just make it 1 in any case. So n is equal to 1, so we have 7 to the power 2 times 1 plus 1 plus 1 is equal to, so 7 to the power 2 times 1 plus 1. 2 times 1 is 2, plus 1 is 3. 7 to the power 3 is 343. So 7 times 7 is 49. 49 times 7 is 343. Plus 1 is equal to 344. And this is equal to 8 times something. 8 times what? 8 times 43. So the base case is divisible by 8 because you got 8 times some number. So now the induction hypothesis, assume true for n is equal to k, where k is some natural number. So this means 7 to the power 2k plus 1 is equal to 8t, where t is a natural number. So any multiple of 8. And we can see how we can manipulate this to look a certain way. So we can say from star, so let's call this equation star. And then we can say from star, we have what? Let's make 7 to the power 2k plus 1 the subject of the formula. 7 to the power 2k plus 1 is equal to 8t minus 1. We might need to use this. So let's see what happens when we move on to k plus 1. So you got 7 to the power 2. So we would have had a k, we have k plus 1 plus 1 plus 1 here is equal to, so we'll have 7 to the power 2k. So when we expand here, we have 2k plus 2 plus 1. So let's write it like this. Plus 2 plus 1. So this is all in the power, in the exponent, and then we have plus 1. Let's just write it this way. So let's write it as 7 to the power 2k plus 1 times 7 to the power 2 plus 1. The reason why I want to do this is because we want to substitute this 8t minus 1 in here. So let's just continue as equal to. So 7 to the power 2k plus 1 we can write as 8t minus 1. And this is times 7 squared plus 1. So what are we going to do here? So 7 squared is 49. Okay, let's expand. So we'll have 7 squared times 8t minus 7 squared plus 1. So this is, and this is equal to, so 7 squared is 49. Okay, let's write it. So it's 49 times 8t minus, so 7 squared is 49 again, and then plus 1 is, so it's minus 49 plus 1 is minus 48. So what's important here is we've got 49 times 8t minus 48. Factor out 8, and then left inside the brackets we have 49t, and then 48 divided by 86, so minus 6. So what we've proven here is that 7 to the power 2k plus 1 plus 1 and then plus the number 1 is in fact divisible by 8. because 8 times this number is a multiple of 8. So we've proven our induction hypothesis. Therefore, 7 to the power 2n plus 1 plus 1 is divisible by 8. And we are done. And thanks for watching.